want to talk now about a case study on regular expressions. So this is getting us much closer to where we really want to go in this course, which is discuss properties of languages and programs in languages and what they mean and all that sort of stuff. So this is the first real case where we're going to do this. Now I'm assuming that you know regular expressions a bit at least. And so the idea of this section is to say, well, let's try and represent regular expressions as, as data, basically, trees in an inductive type, and then we're going to discuss what it means for a string of values, a list of values in this case, to match a regular expression. Right? And if you think about that, the thing that you do with regular expressions is match things, right? And so if you have a formal, understanding of what matching means for regular expressions, you can prove properties of the matching, thing, and you can reason about whether things match or don't match. You can and you really have it all in a formal representation, as opposed to writing a program where you write a regular expression library and you have to test it to see whether it does the right thing. This is going to prove properties of this thing. So let's see how this works. So the starting point is a type called regexp. And the idea of the regexp is it's going to have the constructors will define a language of trees, essentially, that represent regular expressions. And so you can think of this as an abstract syntax tree in a sort of compiler-y sense, but it's really just the same sort of thing as all of the inductive data types that we've been talking about before, except that in this case it has 6 constructors. So there's 6 different constructs that we have to reason about. It's parameterized over some type t, and the reason for that is that the matching process, or how regular expressions work and so on, is really mostly independent of what the underlying things are that are being matched, whether they're numbers or characters or something else's. It doesn't really matter when you're talking about matching regular expressions against sequences of those things. The same meaning applies. So in this definition, the type T is the type of the underlying elements of whatever you're matching. Okay. If you want to think of them as characters, that's the easiest thing, but they could be anything, basically. So that's why you'll see all of these uses of regexp everywhere have T on them, because we're always using the same underlying set of things. And this car one, whose name is suggestive, takes a T. So this is the way of making a regular expression out of a single element of the underlying set. All the other ones are independent of those elements. And these declarations just make it clear that this T is implicit, so mostly you never have to state it explicitly in the definitions. Okay, so that's kind of hard. Well, what do these mean, I guess, is the thing. So informally, in this comment here, you can see there's the sort of informal thing. So if you have a regular expression that's the empty set, then it doesn't match any string. That's essentially, it represents the empty language. Okay. Now, when I say string in this case, what we're talking about is, in this formalization, is lists of things, so lists of T's. Okay, so if you say string, it's really lists of characters, but it could be lists of anything. So empty set doesn't match any string. Empty str matches exactly one string, which is the empty string. Now, this notation is a bit funny. It's the empty list inside that's the empty string. Car x, where x is a T, matches exactly just the sequence containing x, singleton x. Then if you have 2 regular expressions, re1 and re2, and they match some string s1 and some string s2, then app re1 RE1, RE2 matches the concatenation of the string. So this is, in regular expression land, this is sequencing, right? If you put two regular expressions in sequence, then the sequence matches all the things that match the first one, followed by all the things that match the second one in all the combinations that you can have. Union is the choice one, essentially alternation in some versions. So if one of RE1 and RE2 matches S, maybe both of them do, then union RE1, RE2 matches S. Okay, so you can say, well, this matches this regular expression, or it matches this other regular expression using the union thing. And finally, we have star, and this is the iteration. So it's the clean E star in regular expression notation. So if you have RE star, or star RE in this notation, then it matches 0 or more things that RE matches. Okay, so that's what they're saying here. For the non-zero case, essentially, if all of the SIs match the regular expression, then you join them all together, then star, the regular expression, matches the concatenation of all of those things. Star is 0 or more, so it always matches the empty string. Okay, it doesn't matter what the regular expression is, star RE always matches the empty one. Okay, so that's one way of writing down this sort of informal definition. We'll skip over this inductive definition for a second. Another way of writing down things in a more formal way is using inference rules. So that's what this version is saying. And they're introducing this notation E twiddle, or E tilde, to mean S matches RE. So S is a string, RE is a regular expression. Okay, and that's a notation used in some programming languages. So what the rules say is how to sort of define which strings match which regular expressions. So remember, the first one was that the empty set regular expression doesn't match any strings. So we don't have a rule for it because we don't want to say it matches anything. Then we have the empty string matches empty str. A singleton X matches char X. And there are no assumptions here, so these always apply. Right, these are axioms, essentially. And this is sometimes known as an axiom schema because it works for every X that you have. Then this one says if S1 matches RE1 and S2 matches RE2, then the concatenation of the two strings matches app RE1, RE2, the sequencing of the two regular expressions. There are two rules for union because we might have that S1 matches RE1, or we might have that S2 matches RE2. I don't know why it says 2, but if that's the case, then if either of those things are the case, then the string matches the union of the two regular expressions. So for example, you can see from the first one is that if S1 matches RE1, it doesn't matter what RE2 is. It could be anything. Similarly, if S2 matches RE2, it doesn't matter what RE1 is. Okay, and if it matches both regular expressions, then you can choose which one of these rules to use. And in the star case, we have the case, the base case, if you like, where star RE always, the empty string always matches star RE regardless of what RE is. And then we have the iterative case or the inductive case where if S1 matches the regular expression and S2 matches star of the regular expression, in other words, you've got one match and then 0 or more other matches, then you can concatenate S1 and S2 to get 0 or more matches. Okay, so you need both of these because this case here won't work if there are no matches. If the sequence is empty, this case won't apply because this says there has to be at least one string, basically. Okay, so that's a more formal definition in the inference rule sense of what matching of regular expressions means. And then we can take this definition and instantiate it as an inductive proposition in COC, which is what this guy up here is saying. So there's quite a lot of stuff here, but it's all basically just encoding what's down there. So you can see it's X match, it's a prop, and its two parameters are a list of t's for some t and a regular expression over t's, where regex was that the definition we had earlier. So you can think of X match as a binary relation between lists of t's and regular expressions of t's. Right, and that's essentially what this equals tilde is saying. This is a binary relation between strings and regular expressions. So then we just basically encode these rules in constructors of this inductive property, of this inductive relation. So for example, the first one says that the empty string matches empty stir regular expression, which is encoding the empty rule down here. Or this one, which I said was a schema. So it's a schema because we have to say, well, it works for every x, that the singleton sequence x matches the regular expression char x, and so on. So I won't go through all of these, but the app one, for example, says if you pick these things and S1 matches RE1 and S2 matches RE2, then the concatenation of S1 and S2 matches the sequencing of the two regular expressions, which is just the encoding of the mmap rule. So you should look at the rest of these rules and satisfy yourself that they are encoding the rest of these inference rules here. It's a very straightforward translation of those. Okay, so what do we have if we have that? Well, we've got now the ability to reason about regular expression matching. All right, so for example, here's an example that says, well, the sequence containing 1 matches char 1. So in this case, we're using regular expressions defined over the natural numbers, not so the characters, if you like, in quotes, are numbers in this case. So the sequences are all sequences of numbers, right? And this is very easy to prove because we have this mchar, which is saying, well, for everything in T, the singleton list of that thing matches char that thing. So this is just a very straightforward application of that constructor. What about something like a sequence here? So here's a list of 1 and 2, and we'd hope that that would match the sequence of the regular expression 1, char 1 with the regular expression char 2. And that's the case, so we can basically say, well, at this point we need to somehow apply the mmap constructor, right? So one thing you might say was, the only constructor that's going to match this goal is mmap. Right? So if I apply mmap here, it gets a bit confused about what to do, right? So it's basically saying, oh, well, this is an append of lists, but this thing over here isn't an append of lists, it's an actual single list. And this one over here matches because it's just app something something, and this is app something something. So it's getting confused by the plus plus here, which comes from the constructor definition, and the list here. Okay, so one way to do this is to actually be explicit about what's happening. So if we go back to mmap, we'll see mmap has 1, 2, 3, 4 arguments. Okay, and in the usage here, they're using it with 3 arguments, one of which is not filled in. Okay, so what does that really mean? So that if we do that, it's doing the right thing. It's basically saying, well, the first string that we want to deal with this mmap is the singleton 1, and the second string is the singleton 2. This underscore is where the first regular expression would go, which will be char 1, but the apply is able to infer what that regular expression is, so we don't need to give it explicitly. Similarly for the other one, which we don't even have to put the underscore in, it will work that out too. So now we've got two goals. We have to basically show the assumptions of the mmap constructor, which are that the two strings that are arguments match the two regular expressions that are arguments. And that's what we do, again, with mchar twice in this case. Okay, so hopefully this gives you a little bit of an idea of what's going on with the formalization of these things. There's a lot of stuff in this section which I'm not going to spend too much time on, just sort of skim over a few of these things which I encourage you to look at. But I'm just trying to give you the flavor of, we've defined a language, the regular expression language. We've defined a relation between strings, lists, and the regular and programs in the regular expression language, which is the matching relation. And now we're reasoning about that using the techniques that we've used in other examples. Just as one other example that's sort of a bit more meta, I guess, is this theorem. So we can prove that if you have some string in a regular expression, if S matches the regular expression, then it also matches RE star, basically, right? So if you say S matches RE, then S should certainly match 0 or more REs, because this is exactly one RE. Okay, so that's a sort of, again, that's a property of matching that you'd like to have. So once you've defined matching, you've defined regular expressions, you have to go and write down all the desirable properties that you have of these things and show that they actually do hold. So in this case, we can prove that fairly easily. So what's this rewrite going to do? Well, it's going to, so one of the issues we've got here is that the star app constructor is basically using a concatenation over here. So this is going to be one or more. This isn't going to use the 0 repetitions thing because there's something over here, right? But we're going to concatenate to use the star app constructor. We need to have a concatenation on this side. So what this rewrite does is just sticks in an empty string, it's an empty list in there, so that when we do the star app, we get this, right? So the star app is saying, well, no, for this to be valid, this matching has to be valid, then S has to match the regular expression, and the empty sequence has to match the star of the regular expression. That's what M star app says. So the first part is easy because that's our assumption that the S matches the regular expression. And the second one is easy as well because we've got a constructor M star 0, which says that the empty sequence always matches a star of anything. Okay, so that's a meta property, right? So if you're interested in whether you've got your definition of matching correct, then these are the sorts of properties that you want to prove. So I won't spend any time on some of these other ones. There's lots of stuff to get into here, and some of this can take quite a while to do. Feel free to have a look. The main sort of meta point that I want you to get is this is basically an approach that we're going to use quite a bit in what follows in this course. Is we're going to define an inductive type for a language. In other words, the trees that are in that language. We're going to define relations and maybe some functions over those trees, and then we're going to prove properties about how those things work to understand whether our language is behaving the way that we want it to behave, right? And that might be properties about the language, but it might also be properties about particular programs written in the language. So if we wanted to prove, I don't know, that a program always terminates or something, then we can use this sort of approach as well. And we're going to use these sorts of inductive relations to do quite a bit of that as we go through. And we'll see exactly a bit more later on why this inductive relation approach works where a computational approach doesn't work. Lastly, for this week, just as a bit of an aside, I'll just mention two more things, which is one is this remember tactic. So we don't use it too much in this course, but you'll see it occasionally. Basically, the issue with remember is that in something like this, so this is proving that if you have something that matches star of a regular expression and another one that matches the star of the same regular expression, then the concatenation of the two strings matches the star of that regular expression, because you can stick two 0 or more REs together and you still have a 0 or more RE. But the issue is there's a very large induction here. They're doing induction on this H1. Okay. And the problem is that by the time they get after the induction step, there's a bunch of information that's been lost. So talking about it in this comment here, the fact that S1 matched something of the form star RE has gone. And it turns out in this particular proof, which we won't do the detail for, that's quite useful, right? So this is the thing that goes, right? The fact that S1 matches star RE, not something else, is lost in this particular proof. So in the better version down here, they show you that you can use, so this is sort of the same point, you can use the remember tactic to say, well, there's something in my state here, that's star RE, I want to remember it. Basically, it's giving a name to the thing and replacing all the instances of that thing with the name. So in this case, it's RE prime, and all the RE primes are equal to star RE. So it simplifies the goals and things sometimes, and it means that sometimes when you do these tactics, you don't lose the assumption. So see here, this one here, this is the thing that was lost in the first version, right? The string that we're talking about is equal to a star, right? And obviously that can't be the case, right? Star regular expression can't be an empty string regular expression. So that's why a bunch of these proof cases are really easy, because the only case that we're actually interested in is the one where the regular expression is a star regular expression, which is what the rest of these other two cases have to deal with. Okay, so that's the remember tactic. Just replaces an expression in your state with a name and gives you an equality, so you can remember that fact. The last one, way down here. I'm not going to spend too much time on this either, but there's this notion of relating Boolean computation to propositions. We've got this idea, for example, that even B is the same as EV, and we prove all these equivalences and things. And the point in this section is really basically that sometimes that proving that equivalence is a bit messy, and they give you a technique for making it easier to prove those sorts of reflection relations. They call it reflection because it's the relation is being reflected in the computation and vice versa, so they become equivalent. So I'm not going to spend any time on that. If you have any questions about why that might be important, have a look at this section, and we can certainly talk about it. Okay, so finally that's the end of week 6. So have fun with that, and I'll be back in the next video with week 7.